Alright, vectors into space. When we're looking at vectors into space, we have to identify unit vectors. We're going to identify a vector along the x-axis, known as vector I, which has the components 1, 0, and vector j, which has the components 0, 1. Again, I is the unit vector located on the x-axis, and j is the unit vector located on the y-axis. I and j are also called the standard basis vectors in R2. What this means is that you will find these vectors, you can represent any vector located into space with components of I and j, and we will see that in just a minute. First of all, I want you to graph point P, 5, 3 and show that the vector OP, and show the vector OP. What is OP algebraically? So geometrically we're going to represent 5, 3 as such. And if you can see here, this is point P. Now, to create vector OP, O goes from the origin straight to P with an arrow with the head at P. Notice the way it's written, OP, the arrowhead is at P. That's the same thing that you will draw here. Now, this vector OP, okay, is equal to the components 5, 3. But if we want the components in terms of algebraically, we use I and j to represent it algebraically. 5i and 3j will create the vector OP. 5i plus 3j will get us to OP. So, the position vector, where 0, 0 is, O is the 0, 0 from the origin. So not to worry. Now, given a vector A and a vector B, show the following both algebraically and geometrically. So, A plus B. If we're looking at A plus B, we just take component A, which is I plus 2j, and we add the components for B, which is 3i minus 2j. We add those algebraically, and that will give us I plus 2j plus 3i minus 2j, which will result in the answer of 4i. So that is our final vector. If we write that in component form, that will be written as 4, 0. So we can draw this knowing this information. The next part we're going to do is part B. But before we do, we're going to do all the algebraic first, and then geometrically I will show you each of these vectors. So, part B is get 3 vector A. So a scalar multiple of multiplied by 3 times vector A, which gives us 3 times I plus 2j, which will result in 3i plus 6j. Algebraically will give us components 3, 6. Now, let's look at 2a minus b. 2a, 2 times vector A is 2 times I plus 2j. Minus b is minus 1 times 3i minus 2j, and we get 2i plus 4j minus 3i plus 2j. Put the i's together, we get negative I. Put the j's together, we get plus 6j. Put that together, and you will get negative 1, 6 as your components. Let's look at the last one. The last one we have is is absolute of A. Absolute of A is actually asking us to find the length of the magnitude of vector A. To find the magnitude, we just take the x value and square it, plus the y value and square it, and that will give us root 5. The reason why is if you think about vector A, has the components 1, 2 going from the origin. You go right 1 up 2 to get to that the end of the vector. Well, we can create a right angle triangle, and literally it's like doing the Pythagorean theorem. Alright folks, now let's look at this geometrically. We're going to go through this really slowly. So, first of all, we need to have a graph. And basically we're going to graph each one of these separately. So starting with the first one, this is the vector A. And then we have the vector, okay, let's look at this. So part A says vector A plus vector B. Part B says vector 3A, and part C says vector 2A, 2 vector A minus B. So let's just get that in there. 2 vector A minus B. And then D is the components the magnitude of vector A. Alright, so we have vector A, and we need to get A plus B. Okay, so we see that there's vector A here, and now we also need to draw vector B. Vector B is located at 3, negative 2. So here is our vector B. Now, the first part, it says vector A plus vector B. So literally, it's like taking vector B as such that we see here, and what we're going to do is move it so that it's A plus B. To move that, we move it over so that vector A connects to vector B, and that will result in, as you can see, vector A plus vector B will result in, that's right, you see it right here. That will result in the vector going from 0, 0 straight up to this value, and that, folks, is vector A plus B right here. So the one in red is vector A plus vector B. Cool. Alright, so now we've done the geometric interpretation of vector A plus B, and if we look back to our previous answer, we found that vector A was actually equal to 4, 0. If you look back, we had the answer, the component answer for A was 4, 0. And look, when we did it geometrically, we found out that our results will be at 4, 0. And there'd be an arrowhead right here. Let's draw that a little bit thicker so you can see that. There's an arrowhead here. All right. Let's go back and redraw. Let's go back to our A and our B vectors where they were originally. Okay, here they are. Here we're back to A, vector A, and vector B. And now what we want to do is do part B. So we, again, recap. We had for part A, we had the components 4, 0, and we found that algebraically that it's geometrically, it's also 4, 0. Now we want to triple the A vector. So let's look at the A vector and see if we can multiply that by 3. So get 3 of those. Okay, so we're just going to get the vector A and get 3 of those vectors. And we're going to paste 3 of those vectors right after the other. 1, okay, 1, and then again, another one, and we paste them on, and we find out that these 3 vectors, one after the other, will result in, that's your 3A now. Remember that this is your 3 of vector A. We'll have the components here of, and if we read it over, it will be 3 and up 6. And if we look back to the answers that we had earlier, we will find out that yes, we got 3, 6 as our components, and we can show this algebraically and geometrically. Alright, let's go back to our original vector A and B to be able to calculate the next one. Here it is, and remember that we just recap, we just got for 3 vector A was the components 3, 6. Alright, now we now need to do 2 vector A minus B. 2 vector A minus B. So we need to double vector A. So let's do that right now. Double vector A. And we're going to put it on here. This is double vector A. No problem. And once we double vector A, we want to do minus B. So we're going to take the vector B. Okay, we're going to take the vector b and we're going to put them over here, but what we're going to do is turn it around because we want to do minus b. So again, that vector, which was originally going in one direction, is now going in the other direction. Sorry, we're just going to draw him out here. Just carefully so that we don't mess up the way we had it drawn. And we find out that this vector will result in our final result to be at, okay, so we can see here that this is going to be now minus vector b, and minus vector b will result in, if we read the component vector going from 0, 0 straight out to here, we find out that a resultant vector is going to be -1, +6. So that is our final result vector for the last one. So again, for part C, our components will be -1, 6. Really cool. All right, now we're on to the last one. How do you find magnitude using geometrically our answer? And that's pretty simple, folks. So just a moment while we get back to vector A and vector B in its original form. Okay, so here's our A and our B. And the last, so recap for part C, we found the components for part C geometrically was also, funny enough, -1, 6. Really, it's not funny because now we've directly linked algebra to algebraic form of vectors to geometric form of vectors. Now we need to find the magnitude of A. So ignoring vector B, so we're just going to eliminate vector B, and we're going to only find the magnitude of A. To do that, we want to create a right triangle so that we can use Pythagorean theorem. We find that the length here is 1, the length here is 2, all right? And then finally we want to find the length of this side. We use Pythagorean theorem to find the magnitude of vector A. So the magnitude of vector A is equal to the square root of 1 squared plus 2 squared equals square root of 5. And that is the magnitude of vector A. All right, on to the next screen. All right, on to the next screen, folks. All right, now formula for magnitude given a vector x, you would actually end up doing the magnitude of x is equal to the x component, the coordinates of x, so the component value of x squared plus the component value of y squared, in this case is x1 and x2. Basically, it's Pythagorean theorem. Let's look at another example. Example 2. Given x, y, and u having different vectors within 2 space, you're asked to determine the magnitude of x, the resultant vector of 3x minus 2u, magnitude of half of vector u, and the magnitude of 3y plus 2u. All right, with the first one, magnitude of x. Well, folks, just like we just talked about just above there, all we do is take the component vector, the component x component, the y component, and we'd write 2 squared plus 3 squared. And we find the value is root 13. Do the same for 3 vector x minus 2 vector u. This is now algebraic what we have to do, so convert this to the algebraic form, which will be 5i minus 6j, and we put it all together. But don't forget, now we're multiplying by 2. So 3 times vector x, which is 6i plus 9j, minus 2 times vector u, which is minus 10j plus 12j, and we find out that the resultant will be negative 4i plus 21j. Next part. The magnitude of half of vector u. So we can take half, or we can take vector u and take half of all the vector u, the entire values, And then we find the square root of 5 over 2 squared plus negative 3 squared. And you get 61 over 4, which is equal to root 61 over 2. Now don't forget, you can also pull this scalar value out and actually calculate the magnitude of u and then take half of that value at the end. That's another way to approach the same question because we know this through our vector laws we talked about earlier in this unit. Next part, 3i plus 2u, 3y plus 2u. What do we need to do? Well, we need to find what the resultant vector is and then calculate the magnitude. So we can take the component form of the vectors, add the x's, add the y's. Don't forget to multiply by 3 and 2 by their scalar values, and we get 7 components of 7, negative 6, and we find the magnitude of that, and we find out the magnitude of this value is root 85. Okay, on to the next screen. So again, recap all of these values. You should be able to calculate this pretty easily and pretty comfortably. All right, example number 3. You're asked to take A and B and show that vector AB algebraically and geometrically. So let's find the vector. This is A, 1, 5, that's a coordinates. Notice the round brackets. B, which the coordinates are 3, negative 2, and you're to take the vector AB. This is the vector A going to B, and that is the geometric representation. Algebraic represent, now pay attention how we have to understand how AB was created. AB was created from OA and OB. How was this created in this form? It's definitely not OA plus OB. We have to figure out how we got to this. Well, let's see. We know that OA plus AB equals OB. I hope everyone agrees with that statement because OA, tail to head, will create the resultant vector OB. So algebraically, AB was created by the sum, AB was created by, OB was created by OA plus AB is equal to OB. That means that AB was actually created by saying OB minus OA. Hopefully everybody understands where that came from. Again, OA plus AB will equal OB. And that's what I did here. What I want to create is how is AB created? Well, AB was created by OB minus OA to give you AB. And let's look at it geometrically how that was formed. We know AB is here. If I took OB, which is here, and I subtract OA, so here is AB again. Don't forget that it has the same direction and same magnitude as AB. OB is created by taking OB plus OA minus OA. So we take the OA vector, this one, OA vector that's right here, and we bring it minus going in this direction. That's right. And there is our vector OA. But it's going in the opposite direction of our original vector OA because we're doing minus OA. And that's how we would create this vector AB. So AB is equal to the combination of OB minus OA. All right. This is, now don't forget, AB right here is not the position vector because it doesn't start at 0, 0. Position vectors always start at 0, 0. So AB can be translated to this position, and its translation will result in the position vector of AB. So OA plus AB is equal to OB. That means AB is equal to OB minus OA. Now, what is OB? OB is the components 3, negative 2. OA is the components 1, 5. 3, negative 2 minus 1, 5 is going to result in the vector 2, negative 7. And notice here, this vector here is going to be at the point 2, negative 7. It's going to meet at that point. So this is the formula for any vector given 2 points. If you're given coordinates, you take the vector mn is going to equal the x coordinates subtracted, and then the y coordinates subtracted will result in the position vector mn. The magnitude of such, funny enough, will look like something you've seen before. And that's right, folks. This here is the distance formula. So the length of any vector doesn't have to be a position vector necessarily. If I know the actual components of it, will always equal this information because of the distance formula that we learned back in grade 9. Cool. All right, folks, that's the end of this section. Have a numerical day.